You press the flat of a knife against a clove of garlic and it splits open with a soft crunch. Maybe you do this every night without thinking about it, but in that half second, something happens inside that little clove that has nothing to do with flavor. A chemical reaction fires off almost instantly, and it doesn't stop until the garlic hits the heat of a pan or the acid of your stomach. You've been triggering a biological event in your kitchen for years, and most people have no idea it's happening. Garlic doesn't look like it's hiding anything. It sits in a bowl on the counter next to onions and potatoes, waiting to go into a sauce, a marinade, a pot of soup. People peel it, mince it, toss it into hot oil, almost as a reflex. It's one of the most ordinary ingredients in the world, and that's exactly what makes what's going on inside it so strange. Because underneath that papery skin, garlic is essentially holding two separate chemicals apart from each other, like a tiny two-part system that only activates when it's damaged. Here's the part almost nobody thinks about while they're cooking dinner. Whole, uncut garlic contains a compound called allicin, which is completely stable and mostly odorless. Sitting next to it, but separated at the cellular level, is an enzyme called alliinase. As long as the garlic's cell walls stay intact, these two never touch. The moment you crush, chop, or chew a clove, you break those walls open, and the enzyme and the compound finally meet. That contact triggers a fast chemical reaction, and out of it comes a new substance: allicin. This is the compound responsible for that sharp, unmistakable smell that fills a kitchen the second garlic hits a cutting board. Allicin is not just an odor molecule, it's a sulfur-based compound, and it's part of a broader family of sulfur compounds that researchers have spent decades studying for their biological activity. And this is where things start to get genuinely interesting because allicin itself is unstable. It doesn't last. It begins breaking down into other sulfur compounds almost as soon as it forms, and some of those breakdown products are believed to be responsible for many of the effects associated with raw garlic. So, what does any of this actually do once it's inside you? This is where scientists have focused a lot of attention, particularly on the cardiovascular system. Some research suggests that certain sulfur compounds derived from allicin may interact with blood vessels, potentially encouraging them to relax slightly, which could have a modest influence on blood pressure. Other studies have looked at oxidative stress, the kind of cellular wear and tear linked to aging and chronic disease, and found that garlic-derived compounds may have some antioxidant activity in laboratory and animal models. It's worth being careful here. Much of this evidence comes from lab settings or animal studies, and human clinical research shows more mixed and modest results. Garlic is not a miracle switch you flip, but the fact that a kitchen staple contains compounds capable of interacting with blood vessel function at all is remarkable on its own. Now here's where raw garlic and cooked garlic actually diverge, and it comes right back to that enzyme alliinase. Heat destroys it. If you crush garlic and immediately throw it into a hot pan, you cut short the window that enzyme has to produce allicin in the first place. Less allicin forms, which means fewer of those downstream sulfur compounds ever get created. This is not the same as saying cooked garlic is useless. Cooking changes garlic's chemistry rather than erasing it entirely, and heat brings its own benefits, like mellowing the flavor and creating different compounds through browning. But if the specific goal is maximizing allicin formation, raw garlic, or garlic that's been given time before cooking, has a clear chemical advantage. That timing detail is not folklore. It's basic enzyme kinetics. If you crush or chop garlic and let it sit for around 10 minutes before cooking or eating it, you give the alliinase enzyme more time to fully react with allicin before heat shuts the reaction down. Some researchers have specifically pointed to this resting period as a way to preserve more allicin activity even when the garlic is eventually cooked. It's not a trick. It's just chemistry playing out on a timer. In practice, this means the garlic sitting in your kitchen right now can be used a little more deliberately. crushing a clove and letting it rest while you prep other ingredients. Adding raw, finely chopped garlic at the very end of a dish instead of the beginning. Using it raw in something like a dressing or a salsa where there's no heat involved at all. None of this turns garlic into medicine, and it shouldn't replace anything a doctor has recommended. But it does mean the difference between mincing garlic straight into a hot pan and letting it rest for a few minutes isn't just a matter of taste. It's a matter of chemistry. So, the next time you're standing at the counter, knife in hand, about to crush a clove of garlic, it's worth pausing for just a second. That small crunch isn't nothing. It's the starting gun for a chemical reaction that's been quietly happening in kitchens for thousands of years, mostly unnoticed, mostly unexplained, and garlic isn't the only ordinary food doing something like this. Plenty of things sitting in your fridge right now are running their own hidden chemistry every time you cut, cook, or crush them, waiting for someone to ask the right question.